Thank you, Jonathan. So we will start the meeting now. Welcome to this webinar on the topic of chemical recycling. So we will be recording this event and make the slides available afterwards. And if you have any questions, please write them down in the Q&A section in Zoom, and we will attempt to answer them both during the presentation and at the end when we have some time dedicated for this. So I will start with a brief introduction of our organization. ChemSec. We are an environmental NGO aiming to reduce the use of hazardous substances by cooperating with companies, highlighting good examples, opportunities. So we have constructive discussions with policymakers, looking for solutions that are not only beneficial for human health and the environment, but also good for future-proof companies. Our focus is on chemicals, but these last few years, much of the political debate has been held under the circular economy umbrella. Our funding comes from governments and charity foundations, which enables us to keep our integrity. We collaborate and we help companies with phasing out hazardous chemicals, but we also work with investors, providing them with analytical tools to evaluate and reduce investments related to toxic chemicals. So we specialize in the area of chemicals, and we are inspired by our dialogue with progressive brands, many interested and heavily invested in circular economy. And these last 2 years, the political and business views on circular economy has gone from talking nice to getting real. And we all agree that it's not sustainable to go on as we have, business as usual. So things will have to change, and policymakers will have to take uncomfortable decisions. Agile companies will flourish, some will suffer. Brands will have to reconsider their products and business models. And as consumers, we all have to change our behavior and expectations. And it all has its basis in the Circular Economy Action Plan and Chemical Strategy from the Commission. So we need to become circular, and therefore something has to change. We want waste to be used as a resource. We need toxic-free material cycles. We must boost industry that enables all of this. Mechanical recycling is the prevailing method as we speak, but we are being presented by new, innovative ways to recycle plastics, often a bit carelessly referred to as chemical recycling. And there's often confusion about what it means, its limitations, for instance, when it comes to the types of waste that can be treated, but even more so about the ways to calculate and present and market recycled content. So circular thinking, freeing us from, or at least reducing our dependence on virgin material, that must be our focus. If we are to support waste management that is circular and sustainable, we need to be clear about the consequences of the systems that we create. So we must have systems that support real recycling as well as a level playing field. And this goes for all types of recycling. A credible system that can take us from a linear fossil-based thinking, that's what we need. But it will require changes, and it will not support all business models. Brands will have to adapt too. Looking for cheap 100% recycled material, that might not be realistic. A more expensive product made from 50% recycled material, that could in reality be much more circular. I mean, it sounds strange, and it is very complex. And luckily, I have with me two of my colleagues, Jerker and Jonathan, and they will go through the basics of the different technologies, breaking plastics into building blocks. and how we can use mass balance in a way that reflects the actual material, supports different solutions rather than the ones sounding the most amazing. A level playing field in support of circular economy, of change, sorry. So now my colleagues will go through first the different types of technologies to give an overview, and then we will go into detail about mass balance, system boundaries, and what is and isn't included in the calculations. So please, Jonathan.
Thank you, Teresa. So I will give you a short overview of the different technologies and some limitations for them. So when we talk about recycling technologies, we have to start with the mechanical recycling, which is the only recycling technology today that's running at scale. Although only for some streams, for example, PET bottles. There is also some issues with mechanical recycling, loss of quality, for example, and also that there is a problem with not being able to handle contaminated waste streams. But there are new emerging technologies that we will talk about today, and they are under the umbrella of chemical recycling. And I have here separated one of these technologies, the solvent-based purification. It's usually a part of the chemical recycling when we talk about it as a family of technologies, but technically it's not a chemical reaction that's being done during the process. So therefore I've separated them. And chemical recycling is when we break down plastic polymers to smaller building blocks. In solvent-based purification, we only dissolve the plastic material and then reform the polymers again. And I think it's what is important to remember here is the goal of the different recycling technologies is to go from plastic material to new plastic material. So I will start with the material recycling, solvent-based purification. The plastic materials are dissolved in a solvent, and these solvents are suited for the different plastic materials, meaning that they can be very different depending on what plastic you're talking about. And of course, the solvents need to be reused in order to have a sustainable process. This technology can be used for clean monostreams, for example, PET, PE, PP, and other types. And the contaminants can potentially be removed, meaning that we need to know what the contaminants are in order to be able to remove them through purification steps or similar. We have seen that there is a reduced quality of the output material, but it's important to point out here that this is a technology where we have one process for going from plastic to plastic. And there are some examples of this at scale running today. Depolymerization, which is about chemical recycling. So depolymerization is a chemical reaction where we break down the polymer into monomers. And it's done through a solvolysis using methanolysis or aminolysis or similar technologies. And since we have a chemical bond that's being formed in the reaction, we have a potential for byproducts with unknown properties being formed in this process. We can remove contaminants in this process as well, but it still requires purification steps. And we need to know what kind of contaminants we have in order to know how to purify them and remove them. The output is a monomer with usually quite high quality. But the monomer, of course, use or require further processing in order to reach a plastic material. And also for this one, there are some examples of running at a small scale. The next technology is chemical decomposition. First part is pyrolysis. And this is where plastic is heated until it breaks down, resulting in a hydrocarbon mix in the form of pyrolysis oil. This process is sensitive to heteroatoms, for example, nitrogen and oxygen, and can therefore be sensitive to additives into the plastics, for example. And it also means that PVC or other halogen-containing plastics are not suited at all for this. It can theoretically accommodate most kinds of plastics, apart from PVC and others, but it's mostly suited for polyolefins, and the contaminants are removed in the process due to the chemical bonds being broken. And as I said, the complex mixture, that's the output, the pyrolysis oil, can be utilized in existing, for example, naphtha crackers, but it requires further purification, and it requires several steps to reach the plastic material. There is a high energy input needed, and the overall yield of the process is quite unclear, and it's also quite unclear regarding how to calculate the yield. What is the system boundaries for calculating the yield? As with the others, there are some examples of this running at scale, usually connected to a naphtha cracker, where it's used in combination with virgin fossil raw material. So gasification is also a form of chemical decomposition, and it's a controlled process with some oxygen present, where the plastic is broken down into syngas, which is a mix of hydrogen and carbon monoxide, and that syngas can then be converted into monomers and other building blocks to form plastic materials. Similar to pyrolysis, it can theoretically accommodate most kinds of plastics, but it's also most suited for polyolefins. It's less sensitive to heteroatoms, but it's still not suited for PVC. The syngas can, as with the pyrolysis oil, be used in existing plants to produce building blocks. And there are some examples of this. This technology also suffers from the use of very high energy input and unclear overall yield and how to calculate that. So a short summary of some of the general points with all these technologies. So they usually requires clean monostreams or careful pre-sorting in order to, as an input material. And the economic feasibility has not been proven for them. The energy requirements are high, and that of course leads to that the environmental impact has only been partly investigated. There are no complete LCAs being done. There are a lot of question marks regarding what is necessary and what is the requirements regarding energy and other resource use. And that was the very brief introduction to the different technologies. I will now hand over to my colleague Jerker, who will talk more about mass balance and transparency connected to chemical recycling technologies.
Thank you very much, Jonathan. In a circular economy, materials and products are supposed to flow unhindered. However, the material from one single product is in principle never remade into the very same product again, but during the full life cycle, it becomes mixed with other products and materials. To keep track of what comes from where, there are a number of different models how to track different material streams and qualities in products and materials. This is called chain of custody. There are numerous varieties how to count, what to count, and how to tell the customer in the end what the mixed product actually contains. All chain of custody models have pros and cons, depending on where in the supply chain you're situated, from the waste operators all the way to the consumers. Our intention with this graphic is to show a brief overview of 5 of the most commonly used models promoted by different actors, their system boundaries, and the minimum requirements that need to be fulfilled to belong to one or another model. Since there is not yet a developed standard what is what, we have used a slightly simplified language for things to become clearer. So, what about the 5 models and how do they play out when you look at recycled plastics? The first one, segregation, means that all different materials are kept separate all the way from source to product, making it possible to state the exact percentage of the recycled material in any product made from this material. Since it's all 100% pure, all up until the point of when an article is made, this is of course a very thorough way to keep track of different material streams, but it's not frequently used in the chemical industry. The next model, the batch level, makes use of mass balance calculations to keep track of the amount of recycled materials present in every batch of materials. A mixed bag of recycled and virgin materials are blended together to form a batch of material. This batch also becomes the mass balance system boundary. However, since the ingoing masses are known and recalculated for every batch, the correct figure is always known, even if the percentage may differ from time to time. Hence, the batch mass balance can give us just as a correct figure on what is actually present in the finished product as through using segregation, even if it rarely reaches 100%. All the way from recycled material to the finished product, there is a strict physical connection between input and output, and what is claimed is also present. The third model, called site-level mass balance, is sometimes also referred to as controlled blending. Here, the strong physical connection from the previous two models are lost inside the factory, which now form the system boundary, and only the record of incoming mass balanced certified materials are kept. In this way, it allows the producer to be flexible with regard to both when and to which product it chooses to allocate the certified material. The producer is not anymore bound to allocate the certified material in the product which is produced at the time of coming inside of the gates, but can, so to say, save it for a different product where they see an increased interest in the certified product. The mass balance could be calculated on a weekly, monthly, or yearly average basis, depending on the certification scheme. It could be 2% or 20% in that average of the total mass. It all depends on how much was sourced. However, during the defined time of balancing, it may never go below zero. And just to give a calculation example how this could work in practice, say that 20% of the incoming feedstock are certified recycled material. The producer can choose to allocate all of this to one high-end, high-margin product and label it with the claim of being made of 100% recycled materials. This also implicitly means that 80% of the remaining products don't get any label at all. The producer could also choose to label all products with a 20% claim of recycled content. Depending on how the factory is set up and the products produced, in theory, a product labeled as 100% recycled might very well not include 1 single % of recycled material, while at the same time, a product not labeled at all might contain 100% recycled materials. It is hence impossible to know what is actually inside a product with such a claim unless it's further specified. The fourth model, group level mass balance, also referred to extended mass balance, could be seen as an expansion to the site level mass balance, where the system boundaries have been expanded to include multiple sites from the same company group. On the other hand, it can also be considered as an internal, company group specific book and claim model, since it allows the inclusion of recycled material, the booking, to happen in one factory, while the use of the credits, the claim, will take place in an entirely different factory, even in another country. Irrespectively from which angle you prefer to see this model, the basic principle builds on the free flow of certificates and a lack of physical connection between input and output. Finally, the last model, book and claim, is exactly what it sounds like. It is completely void of any restrictions on how materials are booked or claimed. This can occur not only over country borders, but also across continents and between different companies. It's just a certificate which is traded, never the certified material. There is hence not even a theoretical possibility that the end product manufactured with a claim of X% recycled content hold any such material whatsoever. To be overly simplistic, one could state that consumers generally prefer the most conservative method, which in this case would be segregation, whilst chemical recyclers generally prefer the model which gives them more leeway to optimize their existing processes and material flows. Using mass balance to facilitate recycling could be beneficial for companies and consumers, as well as a prosperous circular economy. but this only holds true as long as you don't lose the physical connection between input and output, and that any claims made are not exaggerating the actual content of recycled or certified materials. We have mentioned system boundaries as a defining aspect of these different chain of custody models. As mentioned in the beginning, since there is no standardized way of explaining how to define a product's circular claims, its origin, and its actual content of a certified product, it becomes all important to be precise when any circularity claim are made towards consumers. As an example, we can use a schematic view of how a pyrolysis process works, with unsorted plastic waste coming in on one side, being sorted to pick out only the plastic for which the process is optimized, going into pyrolysis reactor from which the pyrolysis oil is extracted, and to be able to increase the share of pyrolysis oil that can be fed to the cracker, a purification step is often inserted as well. Of course, every step comes with its own losses and generate waste streams, effectively reducing the amount of actual recycled material reaching the cracker. And finally, in the cracker, the recycled feedstock is mixed with virgin feedstock to produce the monomers used to create new plastic items, here represented by an iconic rubber duck. So the question is where to draw the line for a proper system boundary. Should it be here, or here, or here? In the absence of a standard, more or less every company naturally defines their system boundaries as beneficial for their specific processes and products as possible, making a talk about apples and oranges as relevant as never before. There are a number of different unspecified claims connected to various chemical recycling processes, making it sound like the promised land. And they're actually all true, one by one. But the existing techniques can never deliver on all claims combined. The frequent claims we hear in commercials are that our process can use almost any plastic as input material, or our process is very energy efficient. Our process is carbon efficient, rendering a high yield of recycled material. Our process generates products made of 100% recycled materials. Or our process can remove all hazardous contaminants and produce food-grade quality. However, a chemical recycling process which can deliver on all these claims combined is still to be developed. And with this, we would like to open up the floor for a Q&A session. Please write any questions you might have in the Q&A pane, and we'll do our best to answer as many as possible. Thank you very much.
Thank you, Jerker. So I will try to go through the questions that you have put. If you have any further questions, please write them in the Q&A section. There are some questions that have been posted also in the chat question. We will try to raise those as well. I would just like to clarify regarding the chemical recycling and physical recycling. As I said in the talk, we have included the solvent-based purification in this under the umbrella of chemical recycling, because it's usually referred to that. Even if, as I said, there is no chemical reaction being done, it should be, as a definition, not be under chemical recycling, more of a physical recycling or material recycling or similar. But we have chosen to include it here because it's usually included when we talk about different technologies of chemical recycling. So that was a clarification regarding that. So if we can start with the other questions, there has actually been a lot of questions right now, and maybe we can start with one for Teresa. In which area can chemical recycling be useful and complement mechanical recycling?
Thank you, Jonathan. At ChemSec, I mean, we see that chemical recycling is complementary to mechanical recycling, but it very much depends on what type of product you produce, because, for instance, many of these technologies are very expensive. So producing a material that is going to be used for a low-end product, or a product where you depend on that the price is very low, it will become challenging or impossible. So we see that it can be a good solution for specific products. You have to look at your specific product to see if there is any technology that fits for that specifically.
Thank you, Teresa. I can follow up with another sort of overview question. Is ChemSec suggesting that they might consider chemical recycling acceptable in both circularity and climate action policy developments?
Well, there's a simple answer to that, and that's yes. I mean, we do see that chemical recycling has its benefits, absolutely. It's just very important that it is presented in a fair way, and that the pros and cons are clear. And therefore, we do prefer to speak about the different technologies separately, because they do have their specific pros and cons. So the answer is yes, even though, I mean, we do see that it has its limitations, but we will always have the problem of legacy chemicals when it comes to recycled materials. So it absolutely has its place in the circular economy.
So maybe one more question for Teresa. In terms of toxic chemicals, chemical recycling is being claimed as the panache to deal with legacy substances in waste. Once undergone chemical recycling, where do the hazardous chemicals end up?
Mm-hmm. Yeah, that is a very interesting question. And also I would add that, I mean, several of these technologies, it's not like you either clean it or if you don't clean it. There can be traces of it depending on how much you purify the waste. So that's one thing. But of course, we saw that there in the images that Jerker presented, that we do have waste coming out. Of course, these chemicals do not evaporate. They don't cease to exist, but they are extracted from the process. And of course, this waste containing very often hazardous substances must be taken care of in a good way, and it must be accounted for. And therefore, it is also important to draw those boundaries that Jerker also showed very well in the right place. So we actually do include the relevant parts of this flow chart.
So it seems like some people would like a clarification, Jerker, regarding one thing you mentioned. Can you please explain again what they refer to 2 to 20% allocated into the final product? That wasn't clear. What does that mean? Maybe you can clarify.
Yes, certainly. Because if you have a site mass balance approach, then in this case, the 20%, then 20% of the incoming feedstock is allocated as a certified material. And those 20% could be allocated to 20% of all products, or those 20% could be spread out over all products being produced during the same period of time. So the 20% certified material is only the incoming certified feedstock of, say, recycled material. So that is a 20%. It could be 2%. It could be 1%. It could be 0.5%. It could be 50%. So that depends on the site. How much recycled or certified feedstock do they buy and put into the process? And this is the average over time and the allocation time, which is chosen by that company and that specific certification.
Thank you, Jerker. I think it's a very complicated subject, so I think it's good that we clarify that. So thank you. I have one more sort of more policy question. I think that maybe both Jerker and Teresa might answer this one. Given the different methods of chemical recycling and booking, what would you say is the most pragmatic policy option for helping industry to develop chemical recycling so that it can increasingly contribute to circular economy goals?
If I can start there, maybe. I think that the first step is to keep clear definitions of the different types of technologies we're talking about, because as mentioned so many times by us now, we need to keep them apart and treat them as the very different technologies that they are. So one very important thing is to define what is what and speak about it as it is. The other thing is, of course, to agree on how to calculate these things and what we're actually speaking about. So the first steps are all terminology. I would start there. Thank you.
Yes, definitely. And there is a ISO standard on chain of custody being developed to handle mass balance and book and claim in these things. It's being developed. So hopefully that will provide some clarity on how to address these things. But also, I think for me, the most important part is actually that you have a physical connection, that any product being sold as being made out of recycled material actually contains recycled material. And if you claim 100% or fully made of recycled material, whatever phrase you use to implicitly say that this is recycled and it doesn't contain anything, or just a slight small fraction of recycled material, that is not fair play. And it hinders other technologies, because it's easier to, if you can say, if I may use the word cheating, it's easier to cheat than do it properly. So therefore, and that's also the conclusion that in the end, all these different technologies can deliver on one or two of these claims, but none of them can deliver on all yet. There is work to be done. Thank you.
If I can add something there, Jelke, is I also think it is very valid to look at the needs from brands when it comes to communicating this to their consumers, because it needs to be credible, and selling a product that is supposed to contain something that it doesn't, that will not fly in the end. So I think we need to create a system that respects that, but at the same time, like I said, there is also a need for educating consumers that a product containing 50% of real recycled material could actually be more circular than one claiming to contain 100%. So there needs to be a market for lower percentages if this is going to work in that way. And I think that we are able to go there. But this misconception of that 100% recycled material is the only product that there is a market for, I don't believe that that is correct now. And I certainly don't think that it will be correct in the future. Thank you.
Thank you. I should add in the middle of this Q&A section that we have had a lot of questions, so we will not be able to answer all of the questions, but we will answer as many as possible now and maybe follow up on some of the other questions which we will not have time to answer. So next question, I will just post this one to both of you again and see which one wants to answer. How do we ensure that plastic waste that is mechanically recyclable doesn't end up at chemically recycled? What mechanisms do you recommend for that?
I assume that we're talking about the claim that chemical recyclers very often say that they will only take the feedstock that the mechanical recyclers don't want. Yeah, you're nodding, so I think we both see it that way. Yeah, this is a very tricky question. I think that is absolutely necessary, and the chemical recyclers that we have been speaking to, they very much agree that this should be the case, but how to verify this is very difficult, because in the end, what we see is that the level of sorting and the cleanness of the waste is often not very different between mechanical recycled material and the chemically recycled material. So I don't have a solution in hand at the moment, but it's definitely something that needs to be regulated. And it's not very easy to pinpoint how at this stage, but it needs to be addressed, because we see that this is a problem today, that mechanically recyclable material is used in chemical recycling.
Thank you, Teresa. I have one question which I think is interesting. So what is the best waste treatment option for PVC waste? We have talked here that that is a problem, that many of these cannot use PVC. So what would be, is that something that we can chemically recycle, or what would be the best option for that? Maybe Teresa.
Yeah, it's a great question, and one that I've struggled with, because the alternatives are not very good. We do not want to landfill, and we don't want to incinerate. So what do we do with it? There is no technology available that could take care of the masses of, for instance, lead contaminated PVC that we see has come up, and it has a long life. This is a huge problem. And I do think that a technology developed for taking care of all the problematic substances in PVC, making it into new material, that's a very rich company. I haven't seen it yet though. So very curious to see that. But what we see now is that putting contaminated waste into the waste streams, it contaminates also the virgin or the clean material that you use to encapsulate, which means that you contaminate a very high value product that could be high value when it comes into the waste stream again. And we do not believe in this. It rather becomes house fill than landfill, which isn't preferable. So this is our very strong opinion on this. Thank you.
Thank you very much. So another question, which I also think is very interesting, is what do you see as the best way of incentivizing the use of recycled plastics in products? How do we encourage that?
May I?
Yes, you may.
I want to start on the other end, because I do believe that the first thing we need to do is not to push brands into using recycled material, but rather to create a framework that enables toxic-free recycled materials to be available. And then I am quite sure that, to start with, the voluntary approaches from many brands, they are very ambitious. So there is a huge demand for clean recycled material. So that's one thing. And the second thing is that I think you should have discussions with the brands to see what do they identify as the most important ways to incentivize this. But my main message is start earlier, start with creating a system that makes this material available. Thank you.
Thank you very much, Teresa. So maybe a question for Jerker. In terms of overall sustainability, is chemical recycling really an option in view of how energy intensive it is?
As mentioned before, I think definitely chemical recycling is something that is necessary to achieve a circular economy. Definitely, as a end solution for the plastic waste, we can't really handle any other way. But of course, the energy intensity, it's really a problem, especially for the high temperature like pyrolysis and gasification. There's the energy usage. It's a key that has to be reduced in able to be a circular, considered a good and beneficial. Because if it costs more carbon dioxide, for example, to run a pyrolysis process to get the same amount of recycle, then it's a bad thing. So it's possible, but it needs a lot more development, and the processes which are in place today, they cannot deliver on this. Unfortunately not.
Thank you. I see that we also have a lot of questions that have been asked in the chat window, which we have not been followed up, but I will take one from that. What question should a company ask their suppliers to make sure that the recycled material is produced in a credible way? Is there a short answer on that one?
It's difficult. No, it's because for the first question could be, is it certified? There are a number of different certifications. You have Red Cert, ISCC, and so on. So ask for a certificate in the first instance, and then explain then the supplier have to explain what is the chain of custody model used in their certification, because different certifications have different subdivisions. So they have to ask these questions.
Thank you, Jerker. There has been a lot of questions on details, especially regarding, I would say, certification schemes. We will not be able to answer all of them, but that is, of course, a very interesting, and in this case, a very, very important thing, that we have certification schemes that really reflect the content that the producer wants to sell. I see that we have 1 minute left, so I think that we will try to end this webinar. I think it's been very interesting. As I said before, we have had a lot of questions that we have not been able to answer. So there is a lot of interest in this question and in this issue. And I hope that you've all been finding this webinar very interesting, and that you have, if you have any further questions regarding this, we will follow up with that. So I don't know if maybe Teresa, we want to have some final words.
Yeah, that would be really nice. Thank you. And thank you for moderating the question. That must have been quite challenging. Yeah, I just want to thank everyone for attending the webinar. It's great to see that so many people are interested. And like Jonathan said, we will try to answer as much as we can. So if you found this webinar useful, please make sure to sign up for our newsletter if you haven't already. And then you will get invitations to our upcoming webinars and other events. And I do a little promotion here about the next one. Will be on the concept of essential use on the 23rd of June. So I hope to see you then, and thank you very much for attending, and please have a good afternoon. Thank you very much.
Thank you very much.
Thank you and goodbye.